Welcome to this lecture. So, the plan for this lecture is as follows. In this lecture we will discuss about rings, fields and polynomials over rings. So, let us begin with the definition of a ring. So, we denote a ring by this notation R, and it is an algebraic structure. So, namely a set of values. It could be a finite set, it could be infinite set. So, it is a set and there are two operators plus and dot which are defined over the elements of this set. I stress that these are not the integer plus and integer dot, they are just some abstract operations, but for the sake of notation we are using this plus notation and dot notation. So, we will say that this set R along with these two operations plus and dot will be called a ring if all the following ring axioms are satisfied. Axiom number 1, we need the set R to satisfy the properties of an abelian group with respect to your plus operation. Okay. And what are the properties that we require from an abelian group? We need closure property, we need the plus operation to be associative, we require the presence of some special identity element which we denote by this numerical, which we denote by this 0, such that if you perform the plus operation with the element A, you should get back the element A for every element A from the set R. We need the presence of additive inverse and we need the operation plus to be commutative. Okay. So, this is the first requirement from the set R and the operation plus, namely it has to satisfy the properties of an abelian group. The second axiom that we need that the set R should satisfy is the following. We require that the dot operation should satisfy the closure property, namely you take any pair of elements A B from your set R and you perform the dot operation, you should get back again an element from the same set R. We require the dot operation to be associative, that means it does not matter in what order you perform the dot operation on 3 elements, you should get back the same answer, and we demand the presence of an identity element with respect to the dot operation. Okay. So, I denote the identity element if at all it exists by this element 1. I again stress that in abstract algebra this is just a notation, this does not mean numeric 1 or integer 1. So, this element 1 should satisfy the property that if you perform the dot operation with 1 and any group element, any element from the set R, you should get back the same element A. Okay. So, this is the second ring axiom. And the third property or the so called third ring axiom that needs to be satisfied is that your dot operation should be distributive over the plus. Namely, if you take any triplet of elements from the set R, call them as A, B, C, then it does not matter whether you first perform the plus operation on B and C. So, you will get one element from the set R because my set plus my operation plus will satisfy the closure property, and if you now perform the dot operation on the result and A, then the result should be the same as if you perform the dot operation involving A and B, you perform the dot operation involving A and C, and then if you perform the final plus operation. And we need the distributive property to hold both in the left sense as well as right sense, namely we need to satisfy both the left distributive property as well as the right distributive property. So, the distributive property that I had just discussed is called as the left distributive property. We need the dot to be distributed over plus even if dot is after the plus. Okay. So, if all these three properties R1, R2 and R3 are satisfied, then we will say that the set R along with the abstract operations plus and dot constitutes a ring. So, let us see some examples for ring. So, recall our set Zn is the set of integers 0 to n minus 1, and suppose I take two operations here. My plus operation is the addition modulo n, and my multiplication operation is multiplication modulo n, and my claim is that with respect to these two operations my set Zn satisfies all the ring axioms. So, it is easy to verify that indeed the collection 0 to n minus 1 along with the operation addition modulo n constitutes an abelian group. We had already proved it in our earlier discussion, and it is also easy to verify that if we consider the multiplication modulo n operation, then it satisfies the closure property, the operation is associative, and the identity element is actually the numeric one, the integer 1, which is actually present in your set Zn. If you multiply 1 with any element from the set Zn and then take modulo n, you will get back the same element. And it is easy to see that the distributive property is indeed satisfied. That means, you can distribute this multiplication modulo n over plus modulo n, both in the left sense as well as in the right sense. So, that is why all my ring axioms are satisfied, and this ring Zn with respect to the operation plus modulo n and multiplication modulo n is a very special ring, because typically in our computers, in our programming, in our computers we have registers, we have either 32-bit registers, 64-bit registers, or even if you have powerful processors, then you have 128-bit registers, 256-bit registers, where you can save values using either 32-bit or 64 bits or 128 bits or 256 bits and so on. And if you add any two 32-bit number, then again you get back a 32-bit answer and so on. So, if you consider, say for instance, your C programming language, in older versions the integers used to have 32-bit representation, and you add any two integer values, again you used to get back an integer value which can be represented by a 32-bit which can be represented by 32 bits. So, implicitly there the operation that we are performing are addition modulo n and multiplication modulo n, namely if I say int a b and c, and if I perform c is equal to a plus b, then internally I am actually performing a plus b modulo n, where n is 2 power 32 if the integers a, b, c are represented by 32 bits, whereas my n will be 2 power 64 if my a, b, c are represented by 64 bits and so on. Okay. So, this is a very useful ring used in because our internal processors in computers perform operation with respect to addition modulo n and multiplication modulo n, right. So, the next thing that we want to now discuss is the invertible elements of a ring. So, imagine you are given a ring, and if you see closely the ring axioms, it turns out that it is not the case that every element should have a multiplicative inverse. Again, without loss of generality, I am considering this dot operation in the multiplicative sense, but again and again I stress that this is not the usual integer multiplication. So, if you see the ring axioms, it is not necessary that every element have a multiplicative inverse. You need the presence of a identity element 1, but it is not necessary that every element has a multiplicative inverse. So, for instance, if I take this ring Z4, where my Z4 is the collection 0, 1, 2 and 3, then there are several elements which do not have any inverse with respect to the multiplication modulo 4 operation. So, for instance, the element 2 does not have any inverse. You multiply 2 with 0, you get 0. You multiply 2 with 1 and then take mod 4, you get 2. You multiply 2 with 2 and take mod 4, you get 0 and so on. You never get a result which is 1. Okay. So, the element 2 does not have multiplicative inverse here. Okay. So, now what we are going to do is we are going to define a special set which I call as u of r, and U of r is basically the collection of all invertible elements with respect to the multiplication operation. Okay. So, it is the collection of all elements x from your set R, for which you have the guarantee of presence of some element u, such that if you perform the dot operation with x involving x and u, you get back the multiplicative identity element. Okay. And if you have an element x present in the set u r, then the corresponding multiplicative inverse we denote by this notation. Again I stress that this does not mean that I am talking about 1 over x. This is just a representation of the unique value u, which when multiplied with x gives you the identity element 1. Okay. So, let us see some examples of this set u. If I again consider the same ring Zn, then we know that the invertible elements of this set Zn are those elements x in the range 0 to n minus 1, which are co-prime to n. Okay. Because we have proved that multiplicative inverse with respect to multiplication modulo n of a number x exists if and only if x is co-prime to n. Okay. That means, if I consider my n to be a prime number p, then this set u of z p will be nothing but all the elements except 0 in the range 0 to p minus 1, because 0 will not be co-prime to p. Okay. So, now we can prove some interesting properties for this set u of r. We can prove that if you are given a parent ring, okay, and parent ring in the sense that my set u is defined with respect to this ring R, then if I consider the set of all invertible elements from this ring with respect to the multiplication operation, then that collection constitutes a group. Okay. And we are going to prove this. So, it constitutes a group in the sense that it will be actually a subgroup of your set R, okay, because your set u of r will be a subset of your bigger set R. So, basically what we want to prove here is that the collection of invertible elements with respect to the dot operation constitutes a subgroup of your original ring R. And for this, what we have to do is we have to recap the characterization for a subgroup which we had seen in our earlier discussion. So, recall we proved that if you are considering a group, parent group and the dot operation, and if you take any subset H of that parent group, then it will constitute a subgroup with respect to the dot operation if the closure property is satisfied. Okay. If you just prove that a closure property is satisfied, that automatically ensures that all other properties are also satisfied. So, what we have to prove is the following. To prove this theorem, that the collection of all invertible elements of an abstract ring constitutes a subgroup with respect to the dot operation, we just have to prove that your closure property is satisfied in this collection u of r. So, for proving the closure property, we have to show the following. You take any two elements x and y from this set u of r, the element x dot y is also a member of u of r. That is what we have to prove. This is our goal. Okay. And recall, our definition of u of r is that an element is present, an element is considered to be present in u of r if it is invertible. So, basically we have to show that x dot y is also invertible. So, the first thing to observe is that since I am considering that element x as well as element y are invertible, let me denote their multiplicative inverse by x inverse and y inverse, x power minus 1 and y power minus 1 respectively. Okay. Now, my claim here is that the elements x power minus 1 and y power minus 1, they also individually belong to this set U of r. That means, I can say that the element x power minus 1 itself is invertible, and I can say that the element y power minus 1 itself is invertible. This is because the definition of inverse says that if x multiplied with x inverse gives you 1, I can interpret it as if that x inverse. So, here this x power minus 1 is considered as the inverse of x. I can also consider that x is the inverse of x power minus 1. Okay. This is because if b is the inverse of a, then I can consider a as the inverse of b and vice versa. So, that is why I can say that since x is invertible and I have the guarantee of presence of x power minus 1. Similarly, if y is invertible, I have the guarantee that y power minus 1 is present. I can say that both these elements are themselves individually invertible, and hence they also belong to the set U of r. Now, what we have to show, remember our goal is to show that x dot y is also invertible, because we have to show that it belongs to the set U of r. That means, I have to show that there exists some element x dot y power minus 1, which when multiplied with x dot y will give you the identity element. And my claim is that the inverse of x dot y is nothing but y inverse dot x inverse. This is because if you multiply y inverse dot x inverse with x dot y, and then if you use the associative law and then rearrange the terms, you get the identity element. So, that shows that this element is the inverse of this element. Okay. And okay, so the second thing that we have to prove is that this element y power minus 1 dot x power minus 1 is also an element of U of r. Okay. And that simply comes from the fact that we have proved that it is the inverse of x dot y. Okay. So, since we have, so what we are basically saying here is that since I have shown that call this element as capital A and call this element as capital B. Okay. So, what we have shown here is that A is the inverse of B and B is the inverse of A. That means, I can say that both A is an element of U of r because it is invertible, and I can say that B is also an element of U of r because it is invertible, and that is what we wanted to show here. Okay. Right. So, now what we are going to do is we are going to extend our definition of ring to another interesting algebraic structure which we call as a field. Okay. So, a field is an algebraic structure, it is a set of values, and there are two operations, two abstract operations plus and dot, which are defined over the elements of this set F. And we will say that altogether this collection F along with the operation plus and dot is a field if the field axioms are satisfied. So, what are the field axioms? The axiom number 1 is that the plus operation the set F along with the plus operation should constitute an abelian group. Okay. Now, the second property that we demand here is the following: if I exclude the additive inverse, and see I have written down here 0 in quote unquote, it is not the integer 0, it is just a representation for denoting the identity element with respect to the plus operation. So, what I am saying here is that if I exclude the additive identity element, then all the remaining elements of the set F together with the dot operation satisfies the properties of an abelian group. And the third property, the third field axiom that needs to be satisfied is that your dot should be distributive over plus. So, if you see closely these axioms F1, F2, F3 and compare it with your ring axioms R1, R2, R3, you can easily identify that your field is a special type of a ring where every non-zero element is invertible with respect to the multiplication operation. So, remember, recall in axiom number R2, so when we considered the ring axioms, we never demanded that with respect to dot operation all the elements should be invertible and so on, no such demand was there. But now I am putting a demand that okay, I am giving you the liberty, I am giving you the freedom to exclude the zero element in the sense the additive identity element, all other remaining elements should have multiplicative inverse, and if that is the case then I can say that my ring is a field. So, in other words, with respect to the set U that we have defined just now. So, remember U is the collection of all elements which are invertible with respect to your dot operation. So, I will say that my set F is a field if all the elements except the 0 elements are invertible, namely the set U of F is entire set F excluding the element 0. Okay. So, now it is easy to verify that if I consider a prime modulus, then the set of integers 0 to p minus 1, which is nothing but the set Z p along with the operation addition modulo p and multiplication modulo p satisfies the field axioms, because the set of all invertible elements in this collection is the entire collection excluding the numerical 0. So, because here the numerical 0 is actually your additive identity. Now, an interesting property in the field is the following. If I am given a field with an abstract plus operation and an abstract dot operation, and if it is given that the result of x dot y is 0, again I stress this is the abstract dot and this is the abstract 0, do not consider it as to be the usual multiplication and a numerical 0. So, if x dot y is 0, then we can safely conclude that it is either the case that your element x is 0 or the element y is 0. That means, it will never happen that you take two non-zero elements, and if you take that perform the dot operation you get a 0 element, that will not happen in a field. I stress this is true for a field, you can verify this need not be the case for a ring. Okay. So, how do we prove this? So, this is an if then statement, your if condition is this and this is your then part. So, I will give a proof by contrapositive. So, contrapositively, what will be the contrapositive here, since an OR is involved here and you have x equal to 0 or y equal to 0. So, if I put negation in front of this x equal to 0 or y equal to 0, I get x not equal to 0 and OR gets converted into AND, because remember logically if you take negation of A or B, then that is logically equivalent to negation of A and negation of B. So, contrapositively I want to show here, contrapositively I want to show that if x is not equal to 0 and if y is not equal to 0, then x dot y is also not equal to 0. That is what I want to show here. So, let us prove that. So, since x is not equal to 0, okay, and as per the field axioms every non-zero element has a multiplicative inverse. So, let me denote that multiplicative inverse by x power minus 1. Similarly, y is non-zero, so it will have a multiplicative inverse, let me denote it by y power minus 1. Now, as we had proved earlier that if you multiply x dot y with y power minus 1 dot x power minus 1, you will get back the identity element. Okay. That means, I can consider the product of y inverse and x inverse to be the inverse of the element x dot y. That means, I can say that the element x dot y is invertible, and if the element x dot y is invertible, then from the field axiom F 2 we can conclude that the element x dot y was not a 0 element, okay. And that shows that whatever we claimed here is correct. Now, the next thing that we want to discuss here is the polynomials over rings, which is a very important concept used in computer science. So, imagine you are given a ring with some abstract plus and abstract dot operation, and imagine that your dot operation is commutative. Okay. Now, if I want to define a polynomial of degree n over this ring R, it will be of this form. Okay. And this is very much similar to the notion of polynomials that we are familiar with. So, if I say we are very much familiar with polynomial over integers or real numbers and so on. So, if I consider a polynomial of the form 2x square plus say 3x plus 1, then I say that this is a polynomial of degree 2 because the highest power is x square with coefficient 2. We are more or less trying to define the same concept where the here in the case of usual polynomials, the plus operation is the integer plus operation and 2 times x squared should be treated as 2 multiplied with x square. So, we are just extending those plus and dot operation with respect to an abstract ring. Okay. So, that is what is the generalization here. So, we are basically generalizing the existing definition of polynomials that we are aware of with over integers to any abstract ring. So, here we are saying that the polynomial will have the form a n dot x power n, a n minus 1 dot x power n minus 1 and so on, and everything added together. Okay. Since my degree is n, my restriction will be that the coefficient a of n will be non-zero. All other coefficients are allowed to be 0, and each of these coefficients are from your set R, and your plus operation and your dot operation are the ring operations. They are not the integer plus and integer dot operations. Okay. So, now if I consider the set of all polynomials of various degrees that are possible over this ring R, I denote that infinite set by this notation. Okay. So, now my x is no longer in regular parenthesis, they are now within square parenthesis. Okay. So, this is just a notation that you are taking polynomials of degree n equal to 0, followed by all polynomials of degree n equal to 1, followed by all polynomials of degree n equal to 2 and so on. So, it is easy to see that this is an infinite set because I am taking all possible polynomials of various degrees, which is never ending process. Okay. Now, let us see how we define the operations over polynomials over ring. So, we know how to add two integer polynomials, right. So, if I am given two polynomials, say a polynomial 2x square plus 3x plus 1 and say another polynomial 5x plus 2, say this is my a of x polynomial, this is my b of x polynomial. The usual way to add these two polynomials is the following: since there is no term involving x square in b of x, I can imagine that it has some 0 times x square present implicitly. So, that I can now safely assume that both a of x and b of x are of the same degrees, and then I can say that you position wise add the various coefficients. So, 2 plus 0 will give you 2 times x square, then the coefficient of x will be 5 plus 3 and the constant coefficient will be 2 plus 1 3. That is a usual way of performing addition of integer polynomials. We are now extending the same definition to polynomials over abstract rings. Okay. So, imagine you are given two abstract polynomials, arbitrary polynomials over a ring, and for simplicity and without loss of generality, assume that the degree n is greater than equal to m. Now, if n is not equal to m, then as I have done for the case of integer polynomials, I can substitute higher order coefficients in the b polynomial with 0, and then I can safely assume that n is equal to m. Then the way I perform the addition of these two these two ring polynomials is that I component wise take the coefficients of various powers of x from the a polynomial and b polynomial, and I add them where my addition will be now the addition operation over the ring, and of course, these multiply dot operations are the dot operation over the ring. In the same way, I extend my notion of multiplication of two integer polynomials to multiplication of two ring polynomials. So, again what I do here is, if I take the product of two polynomials of degree n and m respectively, the polynomial will be now of degree n plus m, and these will be the various coefficients. Okay. And again I stress that all these plus and dot operations are the dot and plus operations over my ring R. They are not the usual or traditional plus and dot operations. Okay. So, if I denote S of x to be the sum polynomial, then let us denote the coefficients of this sum polynomial to be S of n minus 1 up to S of 0, and it turns out that the coefficient of x power I, which is denoted by S of I, will be nothing but summation of the coefficient of x power I in the A polynomial and the coefficient of x power I in the B polynomial, where the plus operation is over the ring. And in the same way, if I denote P of x as the product polynomial, and if I denote the coefficients of the product polynomial as P of n plus m, P of n plus m minus 1 up to P of 0, then it turns out that the coefficient of x power I will be this expression, where all the dot and plus operations are over the ring. Okay. So, let me demonstrate whatever we have discussed with some example here. So, imagine I consider my ring to be Z3, and my plus operation is addition modulo 3, and my multiplication operation is multiplication modulo 3, and Z3 means the elements 0, 1 and 2. Now, I am taking two arbitrary polynomials. One polynomial is of degree 2 and another polynomial of degree 1 belonging to this set Z3x. Remember, Z3x denote a set of all possible polynomials of various degrees, where the coefficients are from the set 0, 1, 2. Okay. And where my plus and dot operations are addition modulo 3 and multiplication modulo 3. So, now let us see the result of Ax summation of these two polynomials. So, if I sum these two polynomials, so you can imagine that in B of x there is no term with x square. So, you can implicitly assume that you have 0 times x square present. So, the coefficient of x square in the sum polynomial will be 2 plus 0 modulo 3, because the plus operation is plus modulo 3. So, 2 plus 0 modulo 3 will give you 2. Now, the coefficient of x will be 2 plus 1, but now this is not the usual plus, this is now the plus modulo 3. So, that is why the coefficient of x will now vanish, and in the same way the constant coefficient will be 2 plus 1, but now this is 2 plus 1 modulo 3, which will become 0. So, you can now see that the summation of these two polynomials will be 2x square. Whereas, if I multiply these two polynomials, then the coefficient of x cube will be this y x cube. So, this polynomial is of Ax is of degree 2 and B of Bx is a polynomial of degree 1. So, the resultant product polynomial will be have degree 3 at most. So, the coefficients of various powers will be this. Now, 2 times 1 and multiplication here is multiplication modulo 3. So, 2 times 1 modulo 3 will be 2, but now if you see this term, this is 2 into 2 4 and 4 modulo 3 will be 1 plus 2 into 1 will be 2 and 2 plus 1 modulo 3 will become 0. So, that is why the coefficient of x square will become 0. In the same way, this 2 into 2 will be treated as 1, 1 into 1 will be treated as 1 and 1 plus 1 will be 2 and so on. Okay. So, now we can prove here that if my dot operation over the ring is commutative, then if I consider the set of all polynomials of various degrees where the coefficients of the polynomials are from this ring R, then even with the dot operation, namely the product of the polynomials, if I consider this operation, then it will satisfy the and of course, the summation of two polynomials the way I have defined here. So, basically what I am saying here is that if I consider the set of all possible polynomials over the ring, then along with the addition of the polynomials and multiplication of the polynomials, the overall algebraic structure will satisfy your ring axioms, provided the dot operation in your base in your ring R is commutative. Okay. And this can be proved very easily. You can at least see with we have already seen an example here, but it is not very difficult to prove it. We can of course prove the closure property, associative property with respect to the polynomial addition. We can prove the closure property, associative property with respect to the multiplication of the polynomials. The constant polynomial 0, which belongs to R of x, will be treated as an additive identity, because you add the 0 polynomial to any polynomial, you again get back the same polynomial, whereas the element 1, whereas the polynomial 1, the constant polynomial 1 will be treated as the multiplicative identity. Okay. And if you have a polynomial a of x, say with coefficients a of n minus 1 up to 0, a of 0, then it is easy to see that I can find out a corresponding minus a of x polynomial, and minus of a x polynomial will be nothing but minus with it will have coefficients minus of a n minus 1 and up to minus of a 0, where minus are the minus elements are the additive inverse elements with respect to my ring. Then if I perform the addition of these two polynomials, I will get the constant polynomial, namely the 0 polynomial. Similarly, I can find out the multiplicative I can show that my plus operation is distributive over the dot operation, namely the addition of the polynomial is distributive over the multiplication of the polynomials and so on. Okay. So, I am leaving the proof of this theorem as an exercise for you, but it is very easy to prove. So, that brings me to the end of the lecture, today's lecture. These are the references used. Just to conclude, in today's lecture we saw the definition of fields, rings, and we also discussed about polynomials over rings. Thank you.